Hello guys, welcome back to our YouTube channel. I'm Sahil and today we'll be discussing the first 4 problems from the contest Codechef Starters 191. So let's begin. So let's start with the first problem today. The problem statement is divide into 3. So let's quickly read the problem statement. You have n toffees and 3 friends. You will divide the toffees among your friends. You are too generous to take one yourself. You want to make sure that your division is fair, hence you want to minimize the imbalance of your division. Here the imbalance is defined as mx minus mn, where ms is the maximum toffees any friend received, mn is the minimum toffees any friend received. For example, if you're given 3, 1, 4 toffees, your friends, then mx equals to 4 and mn equals to 1, the imbalance is 4 minus 1, which is 3. Return the minimum possible imbalance. So let me quickly explain what is the problem statement. So in the problem statement, you are given a single integer n as input, denoting number of toffees, right? And what you want to do is divide this n toffees amongst your 3 friends. And you want to divide in such a way that the imbalance is minimum, right? So you want to divide in such a way that the imbalance is minimum. So let us suppose say you have your friend 1, you have your friend 2, and you have your friend 3, right? So suppose you give 3 toffees to friend 1 and 1 toffees to friend 2 and 4 toffees to friend 3. So the imbalance here is basically the minimum toffees any friend received, the maximum toffees any friend received. You will just find the difference here. So here the difference is 3. You will obviously take the absolute difference. Difference is 3. So the imbalance here is 3. And what you want to do in this problem is try to minimize this imbalance as small as possible. So I hope everyone has understood the problem statement. Let's quickly read the sample IU as well to understand it a little bit more. So for the first example, we are just given a single integer n3. So if n is 3, it's pretty easy for us to distribute, right? Each of the 3 friends will get 1 toffee each. So the imbalance is 0. Let's look at the second case, 8. In this case, what will happen? So again, I have here my friend 1, friend 2, and friend 3. So what I'll do is I'll give 3 toffees to friend 1, 3 toffees to friend 2, and I have only 2 toffees left with me to give to friend 3. So here the imbalance is obviously 1. I hope the question is a little bit more clear now if you have not understood it before. Fine. So now let's look at the solution. How could we minimize this? So if you observe, the number of friends that we have here are 3. So that is constant. We have 3 friends and we always have to divide this n toffees amongst 3 friends. So one thing is clear, right? If this given n integer, if this is directly divisible by the number 3, then you can evenly distribute all these trophies with your friends, and each and every one of them will get equal amount of trophies, and in that case the difference will be 0. So you will just simply output 0. You will just simply output 0. Again, when will that happen? If your given n evenly divides 3, right? If your given n is evenly divisible by 3, each one of your friend will get equal amount of trophies and the difference is 0. Now let's look at the other case. So if the given n is not evenly divisible by 3, that means you have to give less amount of trophies to any one of the friends and you will have an output greater than 0. So let's see what are possible values that you can get. So let's take an example, 6. So if n is 6, again 6 is divisible by 3. So each of your friends will get equal amount of trophies, that is 2, 2, and 2. Right? So minimum difference here is 0. Now, what if the toffees are 7? In that case, one of your friends will get 3 toffees, other friend will get 2 toffee, and same 2 toffee. So in this case, the minimum difference that we can get here is 1, and if the number of toffees are 8, then we'll have to distribute in this way. So two of the friends will get 3 toffees each, and one friend will get 2 toffee. And in this case as well, the minimum difference is 1. And if you go to 9 again, this will again fall back to the first case, which is 9 is divisible by 3. So each of the friends will get equal amount of toffees, and the minimal difference is 0. So if you observe, we'll have only two possible answers. Either we can divide the n evenly and minimal difference is 0, or we cannot divide the trophies evenly and the minimal difference will be 1. Right? Either the answer will be either 0 or answer will be either 1. Now, how will we determine this when the answer will be 0 and when the answer will be 1? Basically, when we just have to figure out if 3 divides this n evenly or not, right? And how do we check whether a number can divide any other number evenly? We'll just simply do mod 3 mod. We'll check if 6 mod modulus 3. If this is 0, well and good, the minimal difference is 0. If it's not equals to 0, the answer will be 1. I hope the solution is clear to everyone. Let's proceed with coding the logic. So in the input format, we're just given a single integer n. So we'll just take that single n integer and we'll just check now if n modulo 3 is 0. That means if n is evenly divisible by 3, I'll output the answer 0. Else, I'll output the answer 1. Let's see if it will pass the sample cases or not. Let's try to submit this and see. Yes, it's passing all the cases as well. Let's move to our next problem. The problem title is nearest square. Let's read the problem statement quickly. You have a positive integer n. Find the largest positive integer a such that a is greater than or equals to 1 and less than or equals to n. A is a square number, that is a equals to b into b for some integer b. So basically what the problem statement is asking from us is to, in a given range 1 to n, we have to find out the largest perfect square. We have to find the value of the largest perfect square in the given range 1 to n. So if you look at the input format as well, we're just given a single integer t, n, and in sample input we have 3 test cases. 1, the largest perfect square is 1 itself. Now 10, we have perfect square 1, 4 and 9, right? Among this, the largest is 9, so the output is 9. And if the range is from 1 to 48, we'll output 36 as our answer. The problem statement is quite simple. I don't think it's need more explanation. Now, let's proceed with the solution. Now, how can we find what is the largest, how can we find the value of the largest perfect square in the given range n? So there are many multiple ways to solve this problem. I'll just choose the simplest approach for this solution. So what I'll do, I'll just check with each of the perfect square if they are in the given range or not, right? So I'll just check 1. If it is less than or equals to n, yes, then this will be my answer. I'll check next 4. If this is less than or equals to n, yes, this will be my answer. Next, I'll check 9. If this is less than or equals to n, yes, then this will be my answer, right? So this is how I will just check. I will check each perfect square until they are less than n. Now, if for any perfect square, let's say for 16, I find that this is greater than n, I will stop here, and whatever the answer that I previously had, that will be my answer. So a simple linear search with every perfect square. Let's quickly try to code this up as well. So let's read the input format. In the input format, we're just given a single integer t number of test cases, and in each and only line, we're just given a single integer n as input. So you have taken that input, and now for the answer, first I just initialize a answer variable with 1 as the value, and next I'll just simply run a for loop from I equals to 1 till I into I is less than or equals to 1. Right? So this is how I'm checking the condition. This value, this range should be always less than or equals to 1. And while this is true, I'll just simply update my answer to I into I. And at last, simply print my answer variable. Let's quickly check if it will pass all the sample cases or not. Let's try to submit this as well. Cool. That was a very simple problem. I hope everyone is clear with the solution. Let's move on to the next one. So the problem title is add two GCD. Let's quickly read the problem statement as well. You are given two integers x and y. Your goal is to make them have a common divisor which is not 1. That is, there should exist z such that z divides x and z divides y. In one operation, you can do the following: set x to x plus 1 or set y to y plus 1. Find the minimum number of operations needed to achieve your goal. So basically the problem input states that you are given two integers x and y, right? And what you need to do is find the value of z, and this z should be a divisor, should be a common divisor of both x and y, right? And its value as well should be greater than 1. Its value as well should be greater than 1. And let us suppose say for the current x and y there is no common divisor. So what you can do is you can increment the values of x by 1. You can increment the values of y as well by 1. You will do this until you find a common divisor value of z, and you will return that answer. So basically the problem statement is asking us to find the minimum operations needed, so that you find the value of z. Let's look at the sample IO as well to understand the question more clearly. For the first input 2 and 4, 2 is already the common divisor of both 2 and 4, and 2 is as well greater than 1, of course, so we don't need to perform any operations on x and y. The output is 0. Now let's see the next input, which is 1 and 1, right? So 1 is of course the common divisor of both of them, but the value of z as well should be greater than 1, right? So we can't output the answer as 1. So what you can do is increment the value of 1 to 2. Again, still 1 is the only common divisor here, so I'll increment the value of y as well to 2. Now 2 is the common divisor here, so I'll output the minimum operations that are needed here, which is 2. So I incremented 1 one time and x one time, and I incremented y one time, right? Next, let's see the next example, which is 2 and 3. Currently we have only 1 as a common divisor. Now what we can do? So we can as well change the value of this 3 to 4 by incrementing it one time. Now the common divisor is 2, so we'll just output 1 as our answer. That is the minimum moves needed to get the value of z. I hope the problem statement is a little bit more clear now. Let's see how we can solve this problem next. Since the problem is asking us to find the common divisor greater than 1 with the minimum possible moves, so the first thing that we'll try to do here is, for the given x and y values, we'll find the GCD, right? For the given x and y values, if the GCD is coming out to be greater than or equals to 2, then we don't need to perform any operations on x and y, right? We can just directly return this value. Now Next case, if the GCD is not greater than or equals to 2, in that case what we need to do? So I will simply check with two conditions here. Now what are those two conditions? I'll first simply check with x plus 1 y, as I'll perform this operation on x and I'll perform this operation on y as well. So x and y plus 1. If this is not true, I'll check with these next two conditions. I'll try to find the GCD of x plus 1 y or x and y plus 1. Right? If any of these two values is greater than or equals to 2, in that case my output will be 1. In that case my output will be 1 because I am just performing one operation, right? In the first case my output will be 0 because I don't need to perform any operation. Its GCD is already greater than 1, right? Now what is the other case? Suppose, let's say, if the GCD is not greater than or equals to 2 for the first case, and these two cases as well, GCD is not greater than or equals to 2. Now first of all, when will that case happen? When will the GCD not be greater than or equals to even in the second case? This will only happen if both the values of x and y are odd. Let us suppose say this would only happen if both the values of x and y would be odd, right? In that case what would we do? In that case we'll just simply increment the values of both x and y by 1 and now both of their values are even, and 2 will definitely be the common divisor of both these even values. So in this case we can just return here 2. So again, for this problem as well, we just need to check for these three conditions. The first condition, if the GCD is already greater than or equals to 2, in that case we'll just simply return 0. If not, we'll increment x by 1 and check the GCD, and or we'll increment y by 1 and check the GCD. In that case, if the GCD is coming out greater than or equals to 2 in any of the case, then we'll output 1 as our answer. That is, we need to perform one operation. Else, we'll just increment both x and y by 1, and in that case we'll output our answer as 2. That means two operations are needed. Let's quickly try to implement this logic. Let's see the input format. We're just given t number of test cases and then two integers x and y. So let's just quickly take the two integers x and y as the input. Now next what I'll do is I'll just quickly write the code for finding the value of GCD, and for that I'll use the Euclidean algorithm. Now what is the Euclidean algorithm? Euclidean algorithm for finding GCD says that GCD of A comma B is equal to the GCD of B comma A mod B. So GCD of these two values are equal. So I'll just use this formula, this Euclidean formula, to find the answer. So I'll do this while B is not equals to 0. So simply find the value of first A mod B, then store the value of B into A, and then value of T into B. Just return A at last, right? So this is the Euclidean formula for finding the GCD. Cool. Next, we'll follow with our original logic, that is first check if GCD of x and y is already greater than or equals to 2 or not. If that is the case, no operations are needed to be performed and we'll just simply output 0. Else if we'll increment x by 1 and check if this value is greater than, if the value GCD of these two numbers are greater than or equals to 2 or not, or increment y by 1 and check if the GCD of these two values is greater than or equals to 2 or not. If any of them returns yes, then I'll print the answer as 1, meaning we need to perform one operation, right? Else, in the else case, we need to increment both x and y by 1, and in that case I can just simply print the answer directly, meaning I need to perform two operations which would be increment both x and y by 1. Right, let's quickly run the code and see. It's passing all the sample cases. Let's try to submit this. Let's move on to our fourth problem. Let's quickly look at the fourth problem. The title is permuted greater than 2. So the problem statement says that you have an array A consisting of x zeros, y ones and z twos. Check if it is possible to rearrange array A such that a of I plus a of I plus 1 greater than or equals to 2 for each I greater than or equals to 1 less than length of the array A. Print yes or no accordingly. So let me quickly explain the problem statement. So in the input you are given three integers x, y and z. X denotes, the value of x denotes the number of zeros, the value of y denotes the number of ones, and then the value of z denotes the number of twos. Right? And what you need to do is form an array with these zeros, ones and twos such that the sum of any two adjacent numbers should be greater than or equals to 2. The sum of any two adjacent numbers should be greater than or equals to 2. And you can form an array that will satisfy that condition. You will output yes or else you will output no. So if we look at the sample input for this, so in the first case we are given, I'll just write here zeros, ones and twos. This represents the count here. So we have 1 0, 1 1 and 0 2. So this will be my array, right? This will be my array, and we can arrange array in this manner or this manner. In both the cases, the sum of the adjacent numbers is 1 itself, so I will output no for this example, right? Let's look at the next example. So we have 1 0, 1 1 and 1 2 as well. So in this case, if I arrange the array in the following way, 0 2 1, in this sum of these two values is 2, sum of these two values is 3. So yes, I can arrange these numbers in an array in such a way that the adjacent sum of any two numbers is greater than or equals to 2. And if you look at the third example, we have two zeros, 0 ones and 1 2. In that case, this will be a valid configuration, right? This will be a valid configuration. And in the last case, we have 5 zeros, 1 1 and 1 2. So 5 zeros, 1 1 and 1 2 as well. So in this case as well, there is no valid configuration such that the adjacent sum of any two numbers will be greater than 2. So we'll output no for this example. So for this example, the output was yes, and for the last example, the output is no. I hope the problem statement is pretty clear, right? So how can we solve this problem? What do we need to do? So let's try to divide this problem into steps. So for first step, the issue will only arise, this issue of the sum of any two adjacent numbers not being greater than 2, this will only arise when 0 is present, right? So if only ones are present, their adjacent sum will always be greater than, their adjacent sum will always be equals to 2. If twos are present, their adjacent sum will be 4. If the combinations of 1 and 2 are present, their sum as well will be greater than or equals to 2. So this issue will only arise if 0 are present, right? So we need to check if zeros are present, how we can place these ones and twos in the array, how we can place these ones and twos in the array such that the adjacent sum will be greater than or equals to 2. Right? Now, to simplify this problem even more, I will just divide this problem into two conditions. First condition, we have no ones. So count of 1 is 0. 0. So we have only zeros and twos present, right? We have only zeros present and we have only twos present. Now, what would be the valid configuration in this case? So after every 0 we will place 2. After every 0 we will place 2, right? So how many minimum number of 2's do we need here for every 0? If this 2 was not there, it would be still fine for us. The sum is still greater than or the sum is still greater than or equals to 2. So if there are n number of zeros, we need at least n minus 1 twos here. We need at least n minus 1 twos such that the adjacent sum will be greater than or equals to 0 or not. Right? This was the first case. Now next case, if ones are present, right? Count of 1 is greater than 0. Now in this case, what can we do? So zeros are present, ones are present, and twos are present as well. So in this case, to keep the adjacent sum greater than 2, first of all we need to place every 2 after in between these zeros, right? So here 2 should go, here 2 should go, and between 0 and 1 as well we should place 1 2. Between zeros and twos as well, between this 0 and 1 as well, we should place 1 2. So how many minimum number of twos do we need in this case? In this case we would need, if the number of zeros are n in the second case, we would need same at least n twos, right? We would need at least n twos for us to have a valid configuration, and we don't care about this configuration because anyway this adjacent sum will be greater than 2. We need to only worry about zeros in our array and how we can make adjacent sum greater than or equals to 2 using these zeros. So again, to recap, first condition, I just divided this problem to simplify it even more into two conditions. First, count of 1 is 0, so we just have zeros and twos in our array, and for this to form a valid configuration we need at least, for n zeros we need at least n minus 1 twos, right? Second case, count of 1 is greater than 0. In this case what would happen? For n zeros we would need n ones. For n zeros we would need n ones here for us to have a valid configuration. Now the problem statement becomes quite easy. We just need to implement these two conditions. Let's quickly try to code this up as well. So in input format we are given t number of test cases, and in each test case we are given 3 values as input: the value of x, which denotes the number of zeros, the value of y, which denotes the number of ones, and the value of z, which denotes the number of twos, right? And what was the logic that we discussed? First, again we're just dividing this into our two conditions, right? If we have no ones in our array, that means we have y equals to 0. In that case we would need at least, for z number of twos, this value should be greater than x minus 2, right? If that is the case, I will print yes. Else it's not possible to have a valid configuration, I'll just print no. The other case, if ones are present in our array, in that case the count of z should be greater than or equals to x. If that is the case, again I'll print yes. If not, I'll just simply print no. That's it. That was the simple code. Let's quickly try to run this as well. Let's try to submit this. It's passing all the test cases. Thanks for watching this video. If you have enjoyed the content, please make sure to like, share and subscribe for more such videos. See you in the next one. Bye-bye.